Okay. Welcome, everybody, to Explorations in Condensed Matter. The title of this course is Many-Body Entanglement and Tensor Networks. My name is Guifre Vidal, and I'm one of the faculty here at Perimeter. And I thought I would start with some motivation, introduction. So what we want to do in this course is to study many-body systems. And so let me start with a concrete example. One of the Hamiltonians we will study as an example is a simple Hamiltonian which will be given by, it's just the Ising, quantum Ising model. So we'll have sum over nearest neighbors on a system on a lattice. We'll be working on a lattice with n sides. Each side will represent a spin, quantum spin degree of freedom, and we'll have n such quantum spins which interact and which with nearest neighbors and which also see a magnetic field. Okay? So here I'm using Pauli matrices. You are probably more than familiar with those. Let me write them down once. And remember, an important property of these matrices is that they do not commute. That's what makes this problem quantum. And so what we are describing here, this is a very simple model for n interacting spins plus a magnetic field of a strength h. Okay? Very good. So we would like to take this as an example, as a very simple example of a lattice Hamiltonian for a quantum system. We may think that we're in d dimensions. So what we have here is a lattice in d dimensions, maybe 2 dimensions, and we have that on each side there is a quantum spin. And the interactions are as simple as this. And we would like to be able to answer questions about such system. We would like to understand how these quantum spins, we understand them individually, one by one, quite well, but we would like to know what happens when we put them together and let them interact. And so our goal will be to find the ground state. Find ground state, let's call it psi of h, that is the state, the eigenstate of this Hamiltonian with the smallest energy, the eigenvalue. That's the smallest. Okay? It's the smallest eigenvalue of h. And what we know is quantum mechanics gives us all the rules that we need to follow to attack this problem. And in particular, remember that in quantum mechanics, the vector space attached to n spins. So we have n interacting spins. There will be a vector space, complex vector space attached to that, which is going to be given by the tensor product of n copies of the Hilbert space or vector space for a single spin. Okay, so we have this tensor product structure. And computationally, this will have important consequences. The one that we can mention right now is that if we look at the dimension of this Hilbert space, okay, the dimension of the vector space for the n spins is given by, take the dimension of just one of the Hilbert spaces and compute the nth power of it. Okay? So for instance, these are spin 1/2 particles. So for these spins, if it's spin 1/2, then this dimension here is just 2, and we get that this goes as 2 to the n. Okay? What's important here is that this dimension grows exponentially in the number of quantum spins. So every time you add one quantum spin, you have to double the dimension of the Hilbert space, and that will give us a very important computational problem. All right, so a couple of observations. Let me do this here. First one is that typically H, in this case the quantumizing Hamiltonian, is just a crude approximation to both the degrees of freedom that we want to study and their interactions. Okay, so it's not that we've chosen a complex problem to solve. This is the simplest version we could think of. Okay, so it's not that we can further simplify. We believe that's the basic starting point, and we already have a significant computational problem because we have to deal with a Hilbert space of exponentially large dimension. So it's a crude approximation both to the degrees of freedom. We're assuming that we only need to focus on the spin 1/2 degrees of freedom here. Maybe there are many more degrees of freedom around that play some role, but we're assuming that they don't. And then we're assuming also we are simplifying the interaction. We're saying, okay, nearest neighbor spins see each other, next to nearest neighbor, they don't see each other. So we already did our best to simplify the problem, but we still have to deal with an exponentially large Hilbert space. That's the first observation. The second observation is that generically, we do not know how to solve. For instance, how to solve the Hamiltonian. For instance, how to find the ground state. Okay? So you may think, well, that's a computational problem. There are these guys who build very big computers, so what's the big deal? Okay? Well, it's important to recognize that big computers will not solve this problem. Okay? That whenever you have an exponential growth of required computational resources, every time you add a spin, you will have to double the size of your computer. We don't want to study 100 spins. We want to study the thermodynamic limit. We want to have thousands of spins. And there is no way that computers will get there. Maybe quantum computers could do, but I'm talking about classical computers. Okay, but that doesn't mean that we don't try. So over many years, decades, techniques have been developed to tackle these problems. And so let me briefly mention a few. Oh, this is this one. Okay, so we have, generically, we won't know how to solve a Hamiltonian. There might be special cases that we can solve. But let me list briefly strategies, possible strategies. Okay, one is exact diagonalization. So you can think, okay, that's there is a problem if I want to study a large number of spins. But what if I study a small number of spins? I know you already learn about what will happen if I had more. And that's a valid approach. And the only problem that we have is, as I mentioned, that the cost is exponential in the number n of spins. And so in practice, this means that with best computers nowadays and the best exact diagonalization strategies, we can deal with up to 40 spins. Okay? And 40 spins is quite a large number. If you put a spin chain with 40 spins, it feels big. If you try to do it in 2 dimensions, it's not so big, right? 6 times 6, 36, 7 times 7, we're done. So, if you put a 7 times 7 system, that's far, far from the thermodynamic limit. And yet, the supercomputer will not be able to deal with it. Okay? So exact diagonalization will help us learn something when the the behavior of many spins is already reproduced with a small number of spins. If with a small number of spins the system already behaves in a similar way as in the thermodynamic limit, then exact generalization techniques can be very useful. Okay? But typically that won't be the case, and so we will need something else. And this something else could be perturbation. Let me do this here. So this goes up, this goes up. Okay, done. Okay, so another strategy that we could use is perturbation theory. And what this means is we're assuming that there is an exact solution. For instance, a free theory, non-interacting particles. We're assuming that the problem we're interested in, the Hamiltonian we're interested in, is one that has an exact solution plus some perturbation. When this is the case, we can use perturbation theory. And that's also, again, extremely useful. There are many problems that are similar to a free non-interacting particles. You add a little perturbation, and you understand how this perturbation, this small interaction, reorganizes the degrees of freedom, and you can get useful results. The obvious problem with this is that it's only perturbative, which means that generically it may not work when you have a strongly interacting system, for instance, if you use as an exact solution of free theory. Okay, so strong interactions might be a problem. Okay. Now there are other possibilities, and the next one would be to use Monte Carlo sampling. In this case, what we say is, well, we accept that the Hilbert space is very large, but we find a way of actually exploring the parts of the Hilbert space that are of interest by sampling over different configurations of the spins. Okay, so it's a very smart approach, and actually it works very well for a large collection of problems. And here, I'm just being negative today, so I just point out the problems that these methods have. So what I'll point out about Monte Carlo, which I insist is a very useful strategy and technique, is that it has a sign problem, what's called a sign problem, something that people working with Monte Carlo call sign problem, for fermions, for fermionic degrees of freedom, also frustrated magnets, etc. Okay? So when Monte Carlo works, it works fantastic, but there are a number also of very important Hamiltonians that have what is known as the sign problem, which do not allow you to efficiently sample. And so Monte Carlo techniques cannot be used in this important class of Hamiltonians. Okay, and finally, we have variational approaches. And we're talking here specifically of trying to find the ground state of a Hamiltonian. And what we do with variational approaches is that, well, we just discussed that this vector space is too large. Right? We have a dimension of the Hilbert space, which is exponential in n. But what we're going to do is we're going to focus our attention to some submanifold submanifold of dimension, which is, say, order n or polynomial in n. Okay, so instead of exponential, we'll look at a subset of a stage within this huge Hilbert space. Okay, so the picture is that you have this highly dimensional vector space, which is very hard to draw, okay? And with variational approaches, you just decide that you are going to focus on just some tiny subset of states that live somewhere in the Hilbert space, and that today we call this K, okay? And you just ask how much is the Hamiltonian in this submanifold, and look for the state in this manifold that minimizes the expectation value of the energy, and you take that as an approximation to the ground state that you would like. Okay, so variational approaches are such that you cheat from the beginning. You say, I cannot deal with the whole Hilbert space. I'm going to just focus on a subregion of the Hilbert space. And within this subregion, you ask, what's the best state, meaning the one with smallest energy, okay? Very good. So the big problem with variational approaches is that they are biased. Meaning that when you choose this small submanifold of variational states, these states already have some physics with them. Maybe they are, I don't know, magnetically ordered, or maybe they are superconductor. They have superconducting order. And so when you then find the one within this variational class that has the smallest energy, you say, oh, look, I just discovered that this approach gives me a ferromagnetically ordered ground state. Yeah, but maybe you input that information in your variational class, okay? So you might not be learning about the ground state of the Hamiltonian. You are just learning about states, properties of your variational class, okay? So it's biased. What you put in this variational class may be what you get out when you ask the question, what's the ground state of this Hamiltonian? You may not end up with the right ground state. Very good. So what is this? Let's see if I cover this. Yeah, very good. So this course is a 3-week course. See if it works. Yes, we have 3 weeks. And in these 3 weeks, I've divided the 3 weeks into roughly the 3 parts of the course. The first week, this week, we'll talk about the many-body computational challenge. The second week, we'll talk about entanglement in many-body states. And the third week, we'll talk about tensor network states. And let me start by telling you what the third week is about. So tensor network states are variational. It's a class of variational states, okay, wave functions. So we just discussed 4 typical approaches. This falls into the last category, variational approaches. We'll focus on some submanifold in this huge Hilbert space. And we'll try to understand what's the best state within this variational class that approximates the true ground state of the Hamiltonian. So you'll learn that we use some diagrammatical notation to represent the tensor network. You'll see drawings like that, and don't worry, we'll learn what that means. Now, so the ground state is going to be represented with what we call a tensor network. It's an efficient approach. And by this, what we mean is that the cost of simulating n spins is no longer exponential in n, but typically just order n, so linear in the number of spins. Okay? So this allows us to study very large systems. But actually, we can also, exploiting, say, translation invariants, if the Hamiltonian is invariant in the translations, we can also turn them into order 1 cost, which means that the cost does not depend on the system size, which means that we can take n going to infinite and actually deal directly with the thermodynamic limit. Okay? So that's interesting because we no longer need to worry about the system size. We really can go and explore directly the thermodynamic limit without having to account for finite size effects and so on. Good. Another point then is the most controversial one, which is I'm going to declare that this variational class is unbiased. Okay? Tensor networks are unbiased. And they are not, but they are essentially unbiased. What I mean by this is the following. The same tensor network, say the one that I drew before, this one is variational ansatz for ground states of one-dimensional systems, spin chains. The same ansatz can account for all known types of ground states that we know of. Okay, so you give me the Hamiltonian for a spin chain, okay, and we can use the same variational ansatz for the ground state of this Hamiltonian, regardless of what this Hamiltonian is. And that's for a very large class of Hamiltonians. So we know this. We know that this ansatz is essentially unbiased. Okay, it's a variational approach, but we've been able to understand how to account for all possible ground states of local Hamiltonians in 1D in a single ansatz. Okay, so the statement is that we can represent all types of ground states. Okay, and so it turns out that, well, we'll see this the third week. That's where we are trying to get. And in order to get there, we need to go to the second week. The second week, what we'll learn is about the structure of entanglement in ground state wave functions. So we'll look at ground states of local Hamiltonians, okay? And we'll look at what they have in common when it comes to the correlations between different parts of the system. And what we'll learn is that there is something that is known as area law. Okay? As far as the entanglement in the ground state is concerned, there is something that is called area law, which is common to all ground states of local Hamiltonians. And this common feature of all ground states of local Hamiltonians is what was once, and this is known now, it's been known for about 20 years, but only in the last 10 years, we understood how to exploit this property. And that's how tensor networks were developed. Okay? Tensor networks are what happens when you try to exploit this property, which is common to all ground states of local Hamiltonians. When I say all, you can always build counterexamples, but you have to really engineer them, and you could dismiss those counterexamples as not being physical. Okay? So maybe the more correct statement is that a large class of Hamiltonians, local Hamiltonians that we are interested in, they have in common that the ground state fulfills what's known as the area law. Okay? And tensor networks are a way of exploiting this property. Very good. So then let me say that the second and third week, this understanding the structure of entanglement in ground states and also understanding how to exploit it to build tensor network states are the main goals of this course. But the first week will be building tools to be able to study many-body entanglement. Okay, we need to build some tools. Very good. So what tools are we going to see? We're going to see exact diagonalization, which we already understand that it has some limitations, but at least it will get us started, and we'll see what the limitations are and maybe how to, and try to figure out how to overcome them. And we'll also deal with the free fermionic or free fermion formalism, which is just a class of, well, we'll actually understand how to solve exactly solvable theories for, in the case of fermions. So exact diagonalization will give us access to, I said before that we could go to 40 spins, but the techniques that we'll learn this week will actually only allow us to get to around 10 spins. Okay? We'll not try to program a supercomputer or anything like that. We'll just use the laptops. And with the free fermion formalism, we'll go to order 1,000 spins. Fermions. let's say, sites. So we'll be able to deal with a lattice with 1,000 sites, okay, order. All right, and how are we going to do that? We're going to use Julia. Okay, we're going to use Julia language. And in particular, we'll use iJulia, which in turn is based on Jupyter. And Jupyter is some interactive environment or notebook, so we'll be using notebooks. Okay, and I insist that our goal really is to get to week 2 and 3. So you have to survive week 1, but in week 1 we'll learn a bit of how to use Julia and how to use Julia to program exact diagonalization algorithms and also how to solve free fermion problems. Very good, and this knowledge that you get here, you can take it elsewhere, right? If you learn about entanglement structure of many-body states, you have to deal with many-body states. But if you learn to program Julia, or if you learn how to diagonalize, use exact diagonalization, these are techniques that you can bring to many other contexts. Very good. So now, why should you care about all these things? Why should you feel good about having decided to take this course? Well, I don't know. But let me tell you. All right. I want one coming down. So in the end, we'll get to tensor networks and to many-body entanglement, and this is a very active field of research nowadays. And it's at the interface between condensed matter, quantum information, and computational physics. Okay, so this all started with people thinking about quantum information, many-body entanglement, and then that turned into useful computational tools for condensed matter. But the more we learn about condensed matter, we managed to improve the computational tools and so on. And in the end, this is also about viewing condensed matter problems from a quantum information perspective. And so this is all very well connected. So research in this area is very, very active nowadays. If you're looking into starting your career, this is something that you may want to consider. And also, it turns out that nowadays, the impact of tensor networks went beyond solving condensed matter problems. So to give you an example, indeed, it started with condensed matter theory. But nowadays, tensor networks are also used to address problems in statistical mechanics, also quantum chemistry, image compression, and machine learning. And actually also quantum gravity. And in particular also ADS-CFT. Okay, so you can see that it has had an impact on a wide range of research areas as well. So I said this knowledge was portable. You can take it, right? The first week we learn skills that are very useful, but actually you can see that because since tensor networks are being used in all these research areas, that actually learning about tensor networks may also be useful more generally. All right, and I think this is the end of the introduction, and let's get started with Hi, Julia. So do you have your computer on? OK. Can I ask for the screen to calm down, please? Thank you. Okay. So I'd like to ask you to open Jupyter. For me, that means clicking here. And then I also emailed you some notebook. So I'm going to try to find mine, but you should find yours. Let's see. Here. OK. So are we all on the same page? Do you have this notebook on? Anybody who does not have the notebook on? OK, very good. So yeah, that was the title of the course, Many-Body Entanglement and Tensor Networks. So here's the catch. I won't teach you how to program in Julia. You'll just use it. Okay? So we are going to not be very pedagogical. We're going to do it the brutal way. But also, in the end, for us, this is just a tool, not the goal on its own. And so this is, did you have a chance to play around a little bit with the Jupyter environment? Well, that's very convenient. So you've seen that there are cells. You can use, you can move from one cell to the other by going up or down with the arrows, or clicking by clicking on a given cell. There are two types of cells. One is made of text. If you double click on this cell, you can change the text. Okay? And then whenever you're done with the changes, you press Shift Enter. Okay? And it goes back to showing the text. And then we have this other type of cells, which are the code cells. And this one says this is a comment, meaning that this is not going to run this particular line here, because it starts with this symbol. But the next line is a real code line. And so if we're on this cell and we press Shift Enter, something happens. We print whatever is inside the print line command. Now I'm going to change this with my name, which today is John. And I press that, and indeed, we see that we've run the code, the updated code. OK, very good. So luckily, well, no, hopefully you'll have time to play with it maybe later today. Now let me start telling you a bit about how we're going to use iJulia. By representing first numbers, we can represent integers. So we say a is equal to 1. If we Shift Enter that, we get the answer is 1. That's not a very interesting computation, but it shows that everything works. Now we could also, instead of integer numbers, we could deal with real numbers. The difference is that we put this dot in between. So this is 2.3. B is equal to 2.3. And then we ask to make the sum a plus b. So indeed, 2.3 plus 1 is 3.3, as expected. Very good. So we can deal with integer numbers. We can deal with real numbers. And we can also deal with complex numbers. And z equal to a plus b times im. This is imaginary part, or imaginary unit, sorry. So this will give us a complex number. Okay, 1 plus 2.3 im. All right, this is a complex number. Very good. So we can go down a little bit more. Now we started with individual numbers, integers, real or complex. Now let's start working with vectors. So you can see here there is a vector, a 4-component vector with components 1.1, 2.0, 0, 0.2. And this is a row vector. So if we Shift Enter this, iJulia tells us this is a 1 times 4 array of type float 64.2. Well, we'll deal with that. We see the components that we entered. Okay. If you wanted instead to deal with a column vector, this is a row vector. If you want a column vector, then you just need to put this prime here at the end. Okay, so Shift-Enter, and we get, again, it's now instead of a 1 times 4 array, it's a 4 times 1. Okay, so you can think of this as a matrix, which is 1 times 4 or 4 times 1. Yes?
Do you know how to turn off the lights at the front?
Oh.
Do it here, but what do I have to press?
I don't know.
Does anybody else know? I think it would help a lot.
It's something like theme of presentation.
Perfect, thanks. By the way, this is Marcus.
Hey.
And Marcus will be TAing this class. And he knows way more Julia than I do, right? You know a week worth of Julia,
yeah,
and I know a day worth of Julia. So he's the local expert, so you can also ask him questions afterwards. Very good. So we have column vectors, row vectors, and now we can also have a vector made of random numbers, which are complex. So there are two things that we want to learn from this. One is run. Run will generate a random vector or a random matrix in general. So this will be a 4 times 1 matrix, which is, as we saw, 4 times 1 matrix is a column vector. Okay, 4 times 1 means how many rows, how many columns. And we are going to make, we're going to add the imaginary unit times another vector, which will also be 4 times 1. So when we do this, we create a 4-component complex vector. All right? Very good. And now we're done creating vectors. Now we would like to access individual components of a vector. We can do this by square parentheses. So we've just created a vector called W right there. It's this complex vector with 4 components. And if we want to access, say, the second component, we're going to type W and then of component 2 between square brackets. So let's Shift-Enter this. And indeed, we get that this is the second component. You had it here. You see that the precision of the output changes. This is only a presentation thing. So the precision of the way Julius is keeping these numbers is constant. But depending on what format you ask for, you see more or less digits. Very good. So we've seen this. Are there questions? Am I going too fast? Good. So let's see. Let's compute the scalar product. So a scalar product would be, we take a column vector, W. W is a column vector. We multiply it by a row vector, V. We created V as a row vector. So let's multiply them together. OK, and the first thing you see is, well, this is the scalar product that we wanted. But for some mysterious reasons, Julia does not give you a number, but it gives you an array, a 1 times 1 array, with that number inside. OK, that sounds like strange, or it's no big deal. You just need to know that that's the case. So if you actually wanted that number, see, this thing here is a 1 times 1 array. And now we're going to ask for the first component of this array, which is the only number that we have in there. And that will give us the number that we wanted without saying that it's a 1 times 1 array. So if you just want to have a number, not an array, you just have to indicate that you want that component. Very good. More things we can do here. So we can compute the square root of, see, this expression here now is, this was a 1 times 1 array that corresponds to the square norm of W. And we take this number, and now we apply to it the function square root. So this should give us the norm of W, okay? Which is, as expected, the positive number, real and positive. Very good. So this is basic stuff that you need to know in order to deal with vectors. We've done numbers, we've done vectors. Now let's go for matrices. Matrices. Because we're building up the minimum that we need to start there analyzing Hamiltonians. Hamiltonians are matrices, so let's learn about matrices. OK, so I don't know what the comment was here, but let's build a matrix by multiplying this. Remember, this was a column vector, and this is a row vector. So if we multiply a column times a row vector, we get a matrix. This matrix is 4 times 4, and it's full of complex coefficients. We could also create a matrix by using rand n times n will generate an n times n matrix. So in this example, as n is equal to 3, and indeed, when you shift enter this, you get this 3 times 3 matrix. In this case of real coefficients. If you wanted to deal with a Hamiltonian is Hermitian. It means that we have, okay, let me do this as an example. We are here. I'm going to go to insert, and I'm going to type insert cell below. And this will create a cell where there was none, okay? And I'm going to use this to show you what M prime is, okay? So I inserted a new cell between two of the cells that I had. And now I type in M prime and shift enter that. And what I get is, if you look at this, it's the same matrix as before, but with the coefficients, say this element here has been shifted down here. We're shifting columns and rows. This prime is doing the transpose, okay? Transpose, and if this was a complex matrix, then we would have also complex conjugation going on. So it would be the adjoint, okay? If you want to compute the adjoint of your matrix, that is the transpose and complex conjugation of your matrix, then it's this prime. Very good. So what we do in this cell is to say, okay, let's make sure that M is self-adjoint. How do we do that? We take M plus its adjoint. We add those together and divide by 2. The result is going to be self-adjoint. So in this case, because these metrics were real, this means that this matrix is symmetric, meaning that this element and that element are the same. And same thing here. Up here is the same as this one, and so on. Okay, we get the symmetric matrix. Excellent. So we've done numbers, vectors, matrices. Now we're ready to understand or to have a look at how to diagonalize a matrix in this with iJulia. So that's going to be very easy. M is the matrix we want to diagonalize. And there is a function called eigenvalue, eigen something, of M, which will produce two matrices, D and U. Actually, D is a vector and U is a matrix. And so let's shift enter this, and let's look at it. So the result of calling this function on M being a matrix, is there are two objects here. One is a vector, which will contain the eigenvalues of the matrix, and then there is an array, or you could think of this as a matrix, where each column contains an eigenvector of matrix M. Okay? So input a matrix, output the eigenvalues, and the eigenvectors given as columns of this other matrix. So let's check these elements one by one. Indeed, D, right here we assign D and U to these two objects. So D contains the three eigenvalues of the matrix M. And U contains this matrix that we just discussed before, where each column corresponds to an eigenvector of M. Okay, so now suppose you don't, well, you don't trust the system, or you just want to get more familiar with it. So what we can do is to check whether indeed we have obtained the eigenvalue decomposition of M by doing the following. We'll build another matrix N by taking U. I'll discuss this in a second, but basically a diagonal matrix with diagonal entries given by the eigenvalues, and U dagger. Okay? So we're trying to test whether this is true. We're trying to test whether M is equal to U times D times M dagger. We're trying to test whether M is equal to U times D, and this D will be diagonal. In this case, 3 eigenvalues times U dagger. Okay? That's what we would like to check to make sure that we indeed obtain the eigenvalue decomposition. And so what we do is we use this. You can test this. If you have a vector, you can input it in diagonal matrix of this. You put this vector B as the input, and the result, the output, is going to be a matrix with the elements, in this case 3 elements, of the vector in the diagonal. Okay? Very good. So, and now we say display M, display N. We want Jupyter to give us back this matrix corresponding to M, the original matrix, and also N, which is the result of this product, down here. And you can check that indeed they are the same. Okay? You look at them component by component, they are the same. Very good. So you can also display M minus N to see whether they are, how similar they are. And you realize that actually they are not exactly the same, but they differ. This difference is made component-wise. So you take each component of M and each corresponding component of N, and you subtract them. And so you see that the difference of components is 10 to the minus 15, order 10 to the minus 15. You see it here? Okay, so yeah, they are the same up to machine precision. Okay, so they are numerically the same. And yeah, you can compute the norm of N minus N, and you'll see that it's also machine precision, equivalent to 0. Very good. So now the other test that you want to do. So what we're trying to do here is to know, once we decompose, once we have the eigenvalue decomposition of a Hamiltonian, how to deal with the output. Okay. So for instance, now we want to see the same in another way. We're going to check that this expression, well, this expression is true. This expression says, if I have an eigenvector, V1 of a matrix, if I multiply it by the matrix, of course, I expect this to be equal to the corresponding eigenvalue times the vector. And there are a number of things here a bit annoying. That's something that happens when you use Jupyter, or when I use Jupyter. Maybe there is a way to fix it. But this expression should be, I take one of the eigenvectors, the first one, multiply by the matrix, and of course, by definition of what eigenvector is, an eigenvalue is, I should get this thing. I've been calling this D, so let me call it D1. Okay? So we want to check this expression, and we're going to do it by hand. So what we have here is the first eigenvalue. We're going to call it's D1. We're going to call it eigenvalue 1. And then the first eigenvector is going to be, see, we fix, here we're fixing the column, and we take all the elements within the column. Okay, we fix the column to be the first one, and we take all the elements within that column. That's what this is for. So, and this plots, this thing here, if you check the expression we had before for M, for U, sorry, if we go back to U, this corresponds to the first, indeed to the first column, this one here, okay? All right, so this is the first column. And now what we're going to do is we're going to display the result of multiplying M times this eigenvector 1, and also, on the other hand, the eigenvalue 1 times the vector 1, and we hope that the two are the same, and indeed they are the same. Okay? So what you're learning right now is not maths, it's to use iJulia to manipulate individual eigenvectors once you have this eigenvalue decomposition. Very good. Another thing we'll need will be this Kronecker product. So you know that if you have, we're going to be dealing with a tensor product of Hilbert spaces for the spins. So let's suppose we have two spins. We have an operator A acting on the first spin, an operator B acting on the second spin. These are 2 times 2 matrices. A and B are 2 times 2 matrices. And we need to understand how to take the tensor product of those to produce an operator acting on the two spins. And so we're going to do this with examples. I'm going to call capital I the identity on one spin. Okay. I'm going to call X sigma X on one spin. I'm going to call A some particular matrix, 2 times 2 matrix on one spin, which is 1, 2, 3, 4 in components. All right, and what we want to do is we want to learn how to use, or we want to practice the use of cron. Cron is going to take the tensor product of 2 matrices for us. Good, so let's look at this matrix. The cron, this is the cron on 2 matrices I and A, each one being 2 times 2, produces a 4 times 4 matrix, where the structure of this matrix is the one that we expected from the tensor product. So what we do is we look at the identity. We have the identity here. And the first element is 1. So 1 times the matrix that we have next to it, so matrix A, is going to give us these 4 components. Then we go to the next element of identity. We see it's a 0. So this will give us zeros in a 2 times 2 submatrix here. 0 down here again because we have another 0 in the identity. And finally, we have a 1 here. So we'll have another copy of the matrix A right there. Okay, you see this is A and A, 2 copies of A, and 0 and 0. Very good. So you can play around with the other examples. Just get familiar with it. If the first matrix was X, then the zeros are the first block and the diagonal blocks, and the non-zero parts are off diagonal. And then whatever. You can try your favorite combinations and make sure that the results are compatible with what this tensor product should be doing. Very good. And in the last 7 minutes of the class, we're going to go back to the Hamiltonian that we had discussed briefly above. So now we are going to start dealing with a spin chain. We're going to deal this week only with one-dimensional systems, spin chains. And the first thing we want to do is we want to understand how to create a matrix H for the 3 spins, for the Hamiltonian acting on 3 spins. So what's the size of this matrix? 8 by 8. We need to create an 8 by 8 matrix. This is 2 to the 3, right? We have 3 spins. Each spin has dimension 2. Very good. So how are we going to go about this? Well, first, let me do this.
And what is I?
I? It's the identity.
I.
Identity operator. Yes.
No. I mean E.
Oh, that's a function?
It's a function.
They are very funny. So say this again.
So
Can you say this one? I.
Yeah.
You say this one, I, right? Oh, okay. I don't know. In English. But yes. So in Julia and other languages as well, if you want to create the identity matrix, you just type in I and the number is the dimension, and you'll produce identity matrix on that dimension. Okay. We create the sigma X right there. I put the 0 point here to make sure that this matrix is made of real numbers, not integer numbers. If I didn't put the dot, this would be an integer matrix made of integers, and I don't want to have to deal with possible complications later on. So I put just a dot here. Same for sigma Z. Okay. I want the identity on 2 spins. And I want also the tensor product of sigma X, sigma X. That's because I'm starting to build where I need to produce the interaction term, which was up there, which is hidden now, but it was sigma X times sigma X. Okay, so I'm trying to build this type of terms, sigma X here. Very good. So this is the result. If you've noticed, every time you shift enter a cell in a cell, what you get down here is just the expression corresponding to the last line. Okay, so this represents this XX. We don't see the II or the Z or the X, only the last one. Okay, if you get tired of seeing that, you can use semicolon at the end of the expression, and it won't show up when you shift enter that. But at the moment, there is no harm in seeing this expression. They are short, so it's OK. Very good. So here is how we're going to build the XX term, the XX part of the whole Hamiltonian. Okay, this expression. I'm going to explain it in a minute, but you see that it's an 8 times 8 matrix already. So we're trying to get this term plus that term, all the pairwise XX interactions. And the way we do it is by having an XX, so that you can imagine that this is spin 1, spin 2. The XX is acting already on 2 spins. We tensor with identity on the third spin. That gives us the XX term, which only acts on spin 1 and 2, but as an 8 times 8 matrix. Okay. The second term, we do the following. It's the two. We put the identity on the first spin and X on the second and third spin. Okay? And the third term is the X on the first spin, and then the identity on the second, and the X on the third. Okay? So this covers the last term here. So HXX is the way we have, by using this cron, we can build all these interaction terms. Okay? Very good. So what else do we need? Let's also do the magnetic field. And maybe this expression should be clear to you already. So the magnetic field consists of identity on 2 spins and sigma z on another one. And you have it right there. This one is magnetic field on the first spin. This one is magnetic field on the second spin. And this one is magnetic field on the third spin. Very good. So let's shift enter this. And we get some 8 times 8 matrix, as we expected. And so the whole Hamiltonian now will be the sum of these 2 matrices. Okay? So that's all we need to do. We come here and we say H is the sum of these 2 matrices. That's our first spin chain Hamiltonian for a chain of 3 spins. And we're going to eigenvalue decompose it. We are putting together what we just learned a few minutes ago. And what we get is some list of eigenvalues followed by a matrix with, remember, each column of this matrix corresponds to an eigenvector of H. And we're interested in the ground state, mostly. So the ground state will be the eigenvector, the column that you see here, corresponding to the eigenvalue with the smallest energy. So in this case, if you look at the numbers, this is positive, positive, 4. So the smallest eigenvalue appears first. And so the first column corresponds to the expression of the ground state. Okay? It's the eigenvector with the smallest energy. Okay? So the first column will correspond to our ground state. Very good. So let's finish. Let's see, what else do we have to do? We're almost done. So let's do a couple more things, and then we stop for today. So we're going to say we know how to diagonalize one Hamiltonian. Let's diagonalize many Hamiltonians. We're going to introduce a magnetic field. It's going to be, instead of just a magnetic field, we'll have a collection of magnetic fields. I'm not going to explain this in detail. But if you play around with this expression, you'll see how it works. Basically, we have H max gives us the top value of the magnetic field. I equal to 20. Remember, I used to be a matrix. Now I changed my mind. I is equal to a number, 20. That's pretty dangerous, actually, if you do that without being aware of it. And so what we're going to do is we're going to have H. You see here H. H is a collection of numbers ranging from 0 to H max, which you don't see it because, well, you could see it, but H max. So the largest value is going to be 2, right? Let me show you just by changing this. OK, so now we have 10 values only, and you can see them. The values always range from 0 to 2. Let me go back to putting 20. All right, and what we're going to do is we're going to have a loop here. Okay, we're going to initialize the energies This variable here is going to be a vector with 20 values, and we initialize them to be 0. So we have 20 zeros, one after the other. And we'll have a for loop here. Okay, so we'll iterate over I. I will run from 1 to 20, starting with 1. And for each value of I, we'll go and produce a Hamiltonian, which will be a sum of the XX part and the Z part, so the interaction and the magnetic field, with a magnetic field coefficient here, which will correspond to one of the 20 values that we just generated. Which one? Well, the ith one, right? So when I is equal to 1, we take the first value of this 20 list, the 20 components, and and then for that particular Hamiltonian, we eigenvalue decompose it, and we pick up from the eigenvalues, we pick up the first one, which is the ground state energy, as we just discussed. And so what we are doing here is we're collecting the ground state energies for the 20 Hamiltonians that we obtained, right? We're changing the magnetic field in the Hamiltonian. For each magnetic field, we get a different Hamiltonian, and we compute the ground state energy, okay? And we collect the results in this E0 of I. So let's do this. And now if you want to know what we've done, you go to here, E0, and you see the result is a list of ground state energies, okay? And now instead of looking at numbers, which is sometimes hard to visualize, let me just use a plot. We're using PyPlot. Remember, you had to include the package PyPlot. Okay, so using PyPlot, we're going to plot this. We can look at this expression. You can play around with it. Now, for some reason, it's just thinking about how to use PyPlot. This will take a second. And afterwards, if you try to use it again, it will be much faster. So you see it took some time. Let's look at the plot. Okay. I don't have time to change the size of this, but I will change it for the next class. The idea here is that we've plotted what we asked. So what we asked here was plot for all magnetic fields the corresponding ground state energies. Okay? There are two vectors here containing the values on the x-axis and the values on the vertical axis. So with energies as a function of magnetic field. Ground state energies as a function of magnetic fields. We use some marker here. We can change that. We use some color, blue. So we can change this. I don't know. As an example, if instead of a dot, we put O, and instead of blue, we say red, we'll get surprise. Another symbol, which is a bit bigger, with another color. I don't think you want to spend too much time learning about colors, but you can put squares, whatever. Okay. Very good. So we're done, and it's time. Oh, it's even a bit late. So we have spent half an hour learning basic stuff about iJulia. Tomorrow we'll get a bit more serious. Tomorrow we'll take the Eisenhamiltonian again, but we're going to see how to write a code that produces a Hamiltonian not for 3 sides, but for n sides, okay? Generic n. We'll diagonalize it, and we'll also study, start extracting information from this finite system. In particular, we'll look at the critical point of the system, and we'll extract conformal data out of it. So you'll see if you have taken some class in quantum field theory, in conformal field theory, you'll recognize a number of things that you can already, conformal field theory is supposed to be valid in the continuum. For an infinite system, we are dealing with a finite system on a lattice, but you'll see that we can already extract information from this lattice that relates directly to the conformal field theory. Very good. So this is going to be really like a marathon today and tomorrow. Tomorrow in the morning we'll have a lecture, and in the afternoon we'll have a tutorial. And the tutorial will be non-trivial. So if you have some spare time, keep playing around, because it's going to be, we're going to learn a lot by tomorrow afternoon. So what I'm going to try to do is I'll give you the notebook for tomorrow so you can start looking at it again.